All right, so you guys ready to review?
Oh, yes.
Okay. It's like, wait, can everybody hear me? All right. Okay, let's start out with just kind of going over some of the derivative rules just a little bit. Nothing too crazy just yet. So tell me what rule you would use if you wanted the derivative of like y is equal to 3x minus 7 all to the fourth power. So if this is your function, what are you going to do to get the derivative, or what rule is going to apply here?
Would it be either chain or product?
How do you know when the chain rule actually applies or not? Like, when do you know you can use the chain rule versus when you probably shouldn't? Okay, and I do see the chat.
Well, what problem are you doing, Professor?
This 3x minus 7 to the fourth, if you're going to find the derivative, I asked like how to find, or what rule applied, and we said it was the chain rule. And then I asked, how do you know if or when you can actually use the chain rule and when you can't? And so Alyssa says the chain rule would be for more like two or more functions.
Can we do the U, Chad? Right? Or no?
The what?
The U?
The U substitution?
Yeah.
Yeah, that's what we're going to do. I'm asking, like, how do you know when the chain rule applies or not? So we're not going to find the derivative just yet. I want to talk about like when do you know when the chain rule works versus when it's not really going to work. Like, how do you know when you can use it? Okay, then Emily says when the thing in the parentheses is another function itself. Okay, yeah, that's a pretty good answer. Yeah, whenever there's like a function inside of something. So like you've got a quantity that's being raised to the power, or you have a quantity that's inside of your angle, or there's a quantity inside of a radical, but there's some sort of quantity that's being affected by some operation and something other than just X. All right, so with this, since it's just a quantity raised to the fourth power, we can use that, there was that kind of power rule with these types of things. So all it is you just pull the power down. Decrease the power by 1. And then we need to multiply it by something. What do we multiply it by?
The derivative of u, which is what's in the parentheses.
Yeah, the derivative of that quantity inside. So the derivative in that case would be 3. And then the only thing left to do from here is to just multiply any constants together. So your 3 and 4 can just multiply to 12 times 3x minus 7 to the third power. There is your derivative. Okay, let's try a couple more of those, or this type, I guess. So like y is equal to the square root of 7x plus 8. So would the chain rule apply with this one?
Yes.
Yep. Yeah, because you have a quantity inside. So walk me through it. So we know it's going to apply. So
We just take
what?
7x plus 8 as a
Say that
u.
again?
We just take 7x plus 8 as a u.
Okay.
Raise it to the half.
Yeah. So definitely make it an exponent. And that was pretty much just like what we just did. You can pull the power down. Decrease the power by 1, so that's going to be a negative 1/2. And then we're going to multiply it by
7.
7, because that is your u prime. And then just multiply your constants together, so that'd be the 7 and the 1/2. So 7/2 times 7x plus 8 to the negative half. Or what could be another answer? Like this would be perfectly acceptable, but it might not be the actual choice on a free response. Or sorry, multiple choice. Free responses would be totally fine. But multiple choice, sometimes it can give you an alternate answer as opposed to this one. So what would be another equivalent expression?
Would it be 7 on the top and 2 times 7x plus 8, like over in a root, excuse me. Root.
Yeah, you can do that. You could also just leave it to the 1/2 power just on the bottom.
Okay.
Or yeah, change it back into a square root. So any of those 3 answers are perfectly fine on a free response. Just be a little careful on the multiple choice, because if you're saying the derivative is this one, you're correct, but the choice might actually be that one. So you just got to kind of pay attention to what's actually in there. All right, nice job. Yeah.
Can I just ask a question real quick? Sorry.
Mhm.
What equation did you use, or what rule did you use for that one?
For this one that we just did.
Yeah, the one you just did.
So that was the chain rule.
The chain.
Yeah. Is that what you meant?
Yeah, yeah.
For the derivative? Okay, yeah, it was the chain rule. Okay, let's jump into some of the trig functions, because I noticed on the quiz, the trig functions were a little tricky, especially when there was a power involved. Let's kind of work our way up from there. So just to start, what's the derivative of sine?
Cosine.
Cosine.
Sine? Yep. Okay, what if it was sine of 2x?
Then it would it be 2 cosine x?
Close.
Negative 2 sine x.
It's further away. I like the cosine and the 2
Oh,
that
the
was out in
cosine.
front. But what's the angle?
Square x square
2x.
2x. Okay. But
So
if
when
we
you do,
have two, right? Where did the two come from, though? There's two.
so the one outside, like this one.
Yes. Yeah.
So that's coming from the derivative of your angle. So the
Okay.
derivative of the angle goes outside. The derivative of sine is cosine. And then your original angle here stays as the angle in the derivative. And what I see a lot of people do, and it's really easy to get mixed up, is that they want to put the derivative of the angle as the new angle. So they say like cosine of 2. But the angle always stays the same.
Okay.
So if this angle is a 2x, then this angle is going to be a 2x in the derivative. Okay, so now let's change it around a little bit. Let's throw in an exponent. So like sine to the 5th of 2x. So in the notes in the videos, we talked about a technique to find the derivative for this. Do you remember what that was called?
The PTA rule?
Yeah, PTA. And what was what did the P stand for?
Power?
Power. T.
Trig?
And the A.
Angle?
Angle. Okay, so this was a pretty good system to use because otherwise you would have to make like a double U substitution, which is possible. It just gets kind of cumbersome and you can get easily lost in your notation. But if you follow PTA, it really spells out what you're doing and in the correct order. Okay, so the first thing is the power. So it's just like using the power rule. So you're going to pull the 5 down and then decrease the power by 1. So that takes care of the P, or the power. Then you can move on and do the T, or the trig part. So the trig is just the trig function. So don't deal with the power in there, it's just the trig. So the trig function in here is sine. So what is the derivative of sine?
Cosine 2x?
Cosine. And then your angle stays the same. Okay, so that's the trig part of it. And then the A, the angle, now you can look at your angle and go, all right, what's the derivative of the angle?
2.
Okay. And then from there, all you need to do is just like you did in the previous examples, just multiply your constants together. So 10 sine to the 4th, 2x times cosine of 2x. And there's your derivative. Okay, do you have any questions?
Do we
on
multiply
this one?
by 4 or 2? That 5.
This 5
Yes.
by 2.
Okay.
So the 2 times the 5 gives you the 10. Were you thinking the 4 because of the exponent?
Yes.
Okay, so the exponent we already took care of because the original exponent was the 5. So we're not doing a second derivative. And if we were, then yeah, the 4 would pull down and multiply to the 5, but we've already done that. So we don't need to do it again.
Okay. Got it.
Okay, do you have any other questions on this one?
No.
All right, let's just try another one just to make sure we've got it. Let's go y is equal to 3 tangent to the 4th of sine x. So lots of stuff happening in here. So you can still use PTA.
Yeah, we can use, I think.
Okay, so in this case, what's your power?
So it's 4. The power is 4. We times with 3.
Yeah. So if we're going to run through PTA, so the power is 4, what would be the trig function?
It is secant square.
Or what's just the trig function that is in here?
Okay, it's a tangent.
Yeah. And the angle?
It's sine x.
Sine of x. Okay, so yeah, so the power, the 4, that's what's going to get pulled down. So she was right. 4 times 3 gives you 12. I'm going to run out of room. So 12. Decrease the power by 1. And the angle stays the same. So that's just that power part. So now you can move to the trig part of it. So the trig was tangent. So what's the derivative of tangent?
Secant square.
Secant squared. And then finally, what's the derivative of your angle?
Cosine x.
Cosine x. Okay, and that for this one is pretty much it because there aren't really any constants to multiply together. So you can leave it alone if you wanted to. You could delete the multiplication symbol. But that's you are good to go with this one. Just really quick. So this isn't a derivative, this is just an identity. What is sine of 2x equal?
Two sine
It's
x, cosine x.
2
Yeah.
cosine x, 2x. I mean,
Yeah, so sine of 2x is 2 sine x cosine x. Cosine of 2x can be turned into how many different things?
I think
3.
Yeah, 3 of them. What's one of them?
1 negative sine square.
Oh, close. 1 minus 2 sine squared. Or what's another one?
Are these supposed to be in our notes or?
These are
Pre-calc.
supposed to be things that you already know.
Okay, that's what I was thinking.
Yeah, this is from your previous pre-calculus or previous trig class. The things that should
Cosine.
be in your brain.
Cosine squared x minus sine squared x.
Okay. Or what's the third?
Two cosine squared x minus 1.
Nice. Okay, so the reason why to bring these up is because they can be useful. Because if I said, okay, take the derivative of 2 sine x cosine x, a lot of people would just start to go through the product rule, but they don't have to. Like you could actually change it into sine of 2x and then just use the chain rule. Or same thing, if you have one of these 3 quantities, you could change it out into just cosine of 2x and then find that derivative. So sometimes there are more than one way to go if you're kind of paying attention to what's actually there. Okay, and then let's just put everybody's favorite one down. Sine squared plus cosine squared equals
1.
1. Nice. What identity is this one called? Do you remember?
Pythagorean.
Yep, it's a Pythagorean identity. So that's the first one. What's a second? Because there's 3 of them.
Tangent squared x plus 1 equals secant squared x.
Oops. 1 equals secant squared. Okay, and the third?
1 plus cotangent squared x equals cosecant squared x.
Yeah. All right, nice. Okay. All right, let's say you had this as your function or as your equation. Let's go xy plus, let's do cosine of x minus e to the y is equal to 84. So you would be asked to use implicit differentiation with this to find dy dx. So implicit differentiation, that's a little bit different than just a regular derivative. And why is that?
Because it includes
2
y.
variables.
Yeah, it has 2 variables. And so there's something special that you have to do when you encounter like the derivative of a y. So what's that kind of special thing that you don't normally do like in all of those other derivatives?
Multiply it by dy dx for every y that you take the derivative of.
Yeah, you got to multiply by that dy dx every single time you do a derivative of y. And you really do it in these derivatives here, just not all that often. It's really the first thing you do. Like if your function is y equals this, and I said, okay, what's the derivative? The first thing you write down is like y prime, because that is the derivative of y. And y prime, it is the same thing as dy dx. So you are doing it all along. It's just now you have to do it a lot more often, which is sometimes annoying, but it is what it is. Okay, so for xy, what rule is going to apply here to get that derivative? Like we know it's implicit, but we have to start using the other derivative rules that we learned prior.
Product rule?
Yeah, the product rule. So the derivative of x would just be 1 times the y, and then plus the derivative of y would be 1, but I'm doing a derivative of the y. So that's going to be a dy dx. Times x. So all this right here, this is just the derivative of that xy, that first term. Okay. What's the derivative of cosine?
Negative sign.
Negative sign. And then minus, what's the derivative of e to the y?
E to the y.
E to the y. And there's something else.
Dy dx.
Dy dx. Yeah. And then it equals, and then the derivative of 84.
0.
0.
Yeah, just 0. Okay, so here's, I mean, this is all the calculus. So the calculus part's done. Now you gotta do the algebra. So now you gotta solve for the dy dx. So what are you gonna do?
Move.
Isolated on the left.
Mm-hmm. So yeah, everything on the d that has a dy dx, they all stay together. If it does not have a dy dx, move it to the other side. So let's move the sine x over as well as the y. Okay. And from there,
Move dy dx. Factor that out of the
Yep.
left.
factor that out. And then from there, just divide by whatever's in the parentheses. And you're done. All right, let's try this one. Find the slope of the tangent line. Let's just do x plus 2y plus y squared equals 4. At the point 1, 1. So what would you do with this?
Would you take the derivative of the original function and then plug the points back in?
Yeah, we're going to take the derivative. So what on earth tells you to do that? Because it doesn't say, hey, find the derivative and then plug in the point. But there's some other key word that says, oh, this is what it means. So what tells you that you have to do that? What?
Is it the tangent line or the slope?
The slope. Because what is the derivative?
The slope.
The slope. So if it says, hey, find the slope of the tangent line, you are finding the derivative. Okay, so to get the derivative, you're going to have to use what?
The
Implicit differentiation.
Yep, implicit differentiation. All right, so the derivative of x is 1. The derivative of 2y would be
2.
2
dy dx.
dy dx. And then the derivative of y squared.
2y dy dx.
Uh-huh. And the derivative of 4.
0.
0. All right, nice job. So from here, you have a choice. You know, you could do the exact same thing we did up here. Like you could get the dy dx all by itself and get it equal to some expression. And that's totally fine. Personally, I usually don't do that because we're looking for an actual value. So what I do is I just start plugging in my numbers right away because it makes it faster to solve for your dy dx, and then you don't have to try to find this expression first. So I just start plugging in my numbers. So every x is going to become a 1, and every y becomes a 1, just because that's the point. So with this one, that wouldn't be too difficult to do because you only have that one y. But if you've got a lot of x's and y's still in here, then it's pretty advantageous to start plugging in your values. So the y becomes a 1. And so you've knocked out every variable except for the dy dx. And now it's really easy to solve. So just combine your like terms, move the 1 over to the right side, and then divide by 4. And there's your slope of the tangent line. Okay, let's see, do you guys have any questions on implicit differentiation? Okay.
The second derivative on implicit differentiation,
Oh, okay.
is that something you're gonna have maybe on there?
It's like pretty much everything is fair game, so I could. I mean, I might not, but we can definitely go over it. So like
How about higher? Is such a thing as higher, or I was wondering this the other day, is there anything that might be on higher order implicit differentiation, higher than second derivative?
no, like, yeah, I wouldn't
Okay.
ask you to find like a third derivative using implicit.
Okay, all right, good.
That, I mean, it's possible. You could definitely do it. It just gets crazy because, yeah, yeah. I'll just put it as no.
Okay.
Yeah, so implicit, it would just be first and second derivatives, and that's it. Okay, so if we let x squared plus y squared equal 36, so to get the second derivative, we got to find the first. So 2x plus 2y dy dx equals what's it going to equal?
0.
0.
0.
Okay, that is a pretty common error. Is when you do the derivative of a constant that's by itself, like on the right side of the equation, a lot of people just repeat the number. They don't actually find the derivative of it. So just be careful with your constants. Okay, so solve for dy dx. So the 2 would go over to the right side, divide by 2. And so we end up with negative x over y. Okay, so now for your second derivative, what rule, other than implicit, what rule is going to work with this?
Quotient rule?
Quotient rule. Okay, so we know the denominator is just going to be y squared. And then you can just run through the formula. So the low times the derivative of the high, so the derivative of negative x is just -1, minus the high times the d low, or the derivative of the low. So the derivative of the low would be what?
1.
dy dx.
Yeah, 1 dy dx. So we're going to simplify the top a little bit and also do something interesting. So the first term is just negative y, and then the negative becomes a plus. And the dy dx, we don't want to leave it in there. Like, we don't want the second derivative in terms of the first derivative. So we got to substitute out the dy dx. But thankfully, we know what it is because you had to find it right here. So your dy dx, you're going to replace it with your negative x over y. Okay, so now we're at this point. And you can't leave it like this. Like, you can't leave fractions inside of fractions. So what's a nice, quick, easy way to fix this?
Multiply top and bottom by y.
Yeah. Multiply top and bottom by that common denominator. That'll clear out any little fractions. So negative y squared minus x squared all over y to the third. And it's really easy to go, yes, I'm done. However, a lot of times the second derivative is in terms of the original function. So you can simplify it down. So we know x squared plus y squared equals 36. So negative y squared minus x squared is going to equal negative 36. All over y to the third. And if you're asking, do we have to do this? The answer is yes, you do. So once you've simplified your second derivative as far as you can, then look and go, hey, is the original function actually in there? And if it is, and good chance, so it's really high chance that it's going to be in there, you got to fix it. You got to sub it out. All right, that was a good one. Thank you for asking about that. Okay, so let's see, we've talked about product rule. We just did a quotient rule. We've done implicit. We've done chain rule. Oh, let's try this one. How about y equals inverse sine of root x minus 2. Good old inverse trig function from section 3.6. And we're just looking for the derivative. Okay. What would you suggest?
Do we use the derivative inverse trig function, the formula u prime over square root 1 minus u squared?
Yeah. Okay, so in our case, what's the u?
X minus 2?
The
Close.
root, root of x
root.
Oh, root x.
Yeah, the root of x minus 2. So with the inverse trig functions, the u is everything that's inside of the arguments, or like kind of like the angle. So yeah, the u is going to be the root of x minus 2. So then your u prime would equal
1 over 2 of the root of x minus 2.
Yeah. And so that one's found by the chain rule. Just like what we did at the very beginning. Okay, so we have our u, we have our u prime, so now we can just start pulling in the formula. So the u prime, that whole mess can just go right on top. And then underneath, inside that big old square root, is 1 minus u squared. So the square and the square root cancel each other out. So it's just an x minus 2. And then just simplify it down. So inside of your radical, on the bottom, the negative distributes. So you end up with 3 minus x. And then again, you can't leave fractions within fractions. So this is going to simplify down. So basically this denominator just lands down at the bottom. So you have a 1 on top and then a giant mess underneath. 2 root x minus 2 times root 3 minus x. Okay, and just for practice, what is the derivative of arctangent?
U prime over 1 plus.
Okay, so for just arctangent of x itself, like what's actually going to go in the numerator?
1.
And then the denominator is going to be 1 plus
X squared.
x squared. All right. There's one other type of function that we hadn't really done yet, and that was the ln's. It's like y equals ln x minus 1 over x minus 3. And we're looking for the derivative of that.
I'd first rewrite the equation.
Yes. What do you want to rewrite it into?
Y equals ln of x minus 1 minus ln of x minus 3.
Yeah. LNs are really nice functions to work with because they allow you to get rid of quotients, products, random exponents. You can always rewrite them, so it's just like ln of a simple quantity as opposed to like this big fraction. And you don't have to do it, but if you don't, you're going to have to use the quotient rule once you start going through the ln formula, which can be quite the process. So break it apart, and it's a lot easier to deal with.
No, mommy.
Oh, we have a little visitor. All right, what's the derivative of ln of x minus 1?
1 over x minus 1.
Okay, and then the derivative of ln of x minus 3?
1 over x minus 3.
Yeah. Okay, so there's your derivative. So there's the calculus. So then from here, it's just the algebra. So you just combine the two fractions into one. So just get a common denominator.
Which rule did you use for the previous step?
To get the derivative,
Yeah.
just the derivative rule.
Oh, okay.
So the inside goes in the bottom, and the derivative of the inside goes on top. Okay, so then just get a common denominator. So for the first fraction, it needs an x minus 3. Second fraction, it needs an x minus 1. Simplify things down on the top. So the negative distributes. And hey, look at that. The x's on top cancel. So the numerator is just negative 2 over x minus 1 times x minus 3. And you can leave it like this. You can expand the denominator out if you want to, but you don't have to. I personally would just leave it like that because of what's coming in the next chapter. You're going to want to leave it factored. Otherwise, you'll have to just, if you FOIL it, if you expand it, you're going to have to factor it back to where it is. So denominators, just leave them factored. Just nicer to deal with. All right. Very well done. Okay. So you guys have been listening to me for about an hour or close to it. What would you like to ask?
Oh, section 3.7. It's going to be on the exam, right?
Mm-hmm.
I don't know. For me, it was, I know it wasn't assigned, but I did question 19, or I attempted question 19, which is the one where the guy's walking away from the lamppost. And then I also sent you a question in email about the conceptual drawing of similar triangles. Or maybe it was 19, maybe 19 was assigned. Maybe it was a different one. Hold on. Oh yeah, 19 was assigned. 19 was the one I had my question about the similar triangles. And then 21 was, or 20, where was it? Hold on, gotta find it. 29, I think, was the one with the guy walking away from the light. So if you could just talk about the whole similar triangle concept of question 19, that would be helpful for me.
You're talking about the swimming pool?
Yeah, the swimming pool. I sent you an email of a picture of how, because in the calcchat.com, they drew this similar triangle diagram that was very difficult for me to visualize. So I drew it slightly differently, and I wondered if the way that I had drawn it was conceptually correct.
Hmm. Did they draw their similar triangle like this? Or
Not, yes,
vertical?
kind of, yes, yes. They drew it, yours more looks like the pool, how I would describe the cross-section of the pool, but yes, it was very similar to that. And they had the dimension of 2 on the top,
Like right
and then
here?
they had dimension of 12 on the vertical.
So 2 on this one?
Yeah,
And then, okay, so this is definitely not drawn to scale.
right. And yeah, that's what I was saying. It was very similar to what you drew, but and I drew it differently.
So they had a 2, or was it 3?
No, exactly. That's exactly why I had to redraw it, because I couldn't. I think what they did was they drew. If you look at the, are you able to look at the email I sent you where I put the picture of what I drew in there?
Let's see.
Because it's gonna be really difficult to describe.
Did you just did you send it right before this stuff happened?
I sent it this morning.
There it is. Okay.
Yeah.
Try. It's 1, 2. Okay. And you have 12. 1, 2. The 1. Oh, I see. Okay, so theirs would be right, because if you actually make it a 3, it's no longer you wouldn't have that triangle anymore.
Exactly. Which triangle? The upper. So in my drawing, there's an upper and a lower triangle. And I
Yeah.
was kind of visualizing the lower triangle superimposing over the upper right-hand side of the top triangle.
Okay. Yeah.
I didn't know if those angle assumptions that I made were geometrically accurate.
The angle assumptions.
Yeah, like I have the right angle on the two triangles, and
Mhm.
then there's the angle, the smaller of the two acute angles in the upper right-hand corner of each triangle. I didn't know if I could
Okay.
consider X and C parallel in my drawing.
It's like it could, like the assumption that would have to be like,
Right. Yeah, are they parallel?
wait, this is not. It's like if you're assuming that these are both like the different water level heights, then that would be correct. As long as this is the part that's in the triangular portion of the pool, as opposed to the rectangular top. If that was the case, then yeah, these two lines would definitely be parallel to it.
Oh, I think I understand their drawing now. The one that's the top one with the 2 and the 12. Did
Mhm.
they draw the horizontal line 1 meter down from the top and
Yeah.
make that triangle? Is that what they did?
Yeah.
Oh, okay. And then they flipped it on its side, which makes it really confusing.
Yeah. I don't know why they chose to do it that way, but they did.
Because when they flipped it on, that's where I'm struggling, is because they flipped it on the side.
Yeah. I would have drawn it kind of like how you have yours, where it's still the
Yes,
same
sideways.
orientation.
Yeah. So 2 is to 12 as 1 is to H. I see. Okay, now I see it. Okay, yeah, I see it
Okay.
now. With the, I don't know if I sent you the bottom drawing with the 6H in it. But in that drawing, I'm able to better correlate the flipped image that they created.
Okay. Yeah. I would agree.
Not the middle image. My drawing, I think my drawing is kind of okay, the middle one, because
Mhm.
it's 1 meter and 1 meter. It's 1 meter deep of
Yeah.
water and it's 1 meter high on the rectangular portion of the trapezoid. So
Yeah.
I think in this particular case, it works because they're both 1 meter.
Yeah.
But if the water had been 1.5 meters deep, that wouldn't have worked.
Yeah.
Okay, yeah, the book did a really hard time. The book made it really difficult on that one for me to visualize.
Yeah. CalChat is really is interesting sometimes in how they do something. It's like, I get what you're doing, but that's not the normal everyday approach to it.
How would you have approached 19?
I
That
think pretty
problem,
much
that
like
whole problem.
what you're doing, and how you do. I would have drawn it I wouldn't have drawn it this way for certain. But I would have approached it, I think, pretty much like what you're doing.
The bottom one,
Yeah, I think so.
not the middle one. The middle one, no.
Yeah, not the
Okay.
middle one. So like kind of
No.
like like theirs and yours kind of merged together.
Yeah. Did anybody else have a problem with 19?
I'm guessing so. 19 is tricky. But I will tell you that I'm not giving you one that tricky on the exam.
Oh yeah, because then they
Yeah,
limited the
always
value.
that I had,
Oh, go ahead.
that I had tried the one of the man walking away in the shadow and just found it, yeah, pretty tricky and not, I think, comparative in difficulty to like doing the baseball diamond or the cone filling, with water. But I am noticing some comments in the chat that it'd be great if we could maybe just do like a 3.7 problem together for review, as well as implicit differentiation.
Yeah, more implicit differentiation.
Yes, please. I have an example, or I have a problem from the homework, number 7. It's x e to the y. Oh, sorry. I think my screen froze.
Oh, actually, it might have been mine.
Okay.
I sent you an email with number 5 and number 7.
Oh, perfect. Okay, thank you. I'll take care of that myself then.
Okay. Let's how about let's do number 21. 21 is a good one because it's got kind of like a bunch of different ways you can ask the problem, or you can find different things on the same scenario. So you have a ladder 25 feet long leaning against the wall of the house. So it makes a right triangle because we're assuming that the wall of the house is perpendicular to the ground. Otherwise, it would be a weird house. So we've got a right triangle, and we need to start labeling your sides. And again, you can label them as to whatever variables you want. Personally, I stick with X and Y, but you can use whatever you want. And X to me is always going to be a horizontal side because that's like the X axis. And anything going up and down or vertical is going to be a Y. But if you want to use F and G or I and Q, totally go for it. Now, the ladder, I see a lot of people, they want to label it as Z. They want to make it a variable, but it's not. How come it's not a variable?
It's a constant.
It's a constant because they told you that the ladder is how long?
25 feet.
It's 25 feet. So the ladder is not changing in length. So it's always going to be a length of 25. What is changing is the height, or the point where the ladder is moving down or sometimes moving up. So the vertical side is changing, and the base of the triangle is also changing, the X, because the base of the ladder is either getting shoved towards the wall or shoved away from the wall. So this side's also changing, but the ladder's not. It's just a constant 25 feet. Okay, so for the no, like what, let's see, they want how fast is the top of the ladder moving down the wall when its base is 7, 15, or 24 feet from the wall. So what might be a good formula that would apply in here? One that you already know, like prior to coming into the class, what formula would go really well with this?
X square plus y square equal to 25.
Yeah, just the good old Pythagorean theorem. Okay, your givens, this would be the stuff that the problem actually gave you. So we know one of them, the ladder is 25 feet. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So right there is another given, but what is it that they gave you? Like they gave you 2, but how do you label it?
dx over dt.
Yeah, dx over dt. Because it's this side that's changing at a rate of 2. So anytime it's a rate, it's d this letter over dt. And then they also gave you, we'll just do one of them. We'll do it when the base is 7. And what do they want you to find? How fast is the top of the ladder moving down? So that means you're trying to find what? So this top of the ladder moving down.
dt.
Yeah, you're trying to find dy dt. Okay, so if you're trying to find dy dt, where are you going to get it? Because it's nowhere in here. So how the heck are you supposed to find it if it's not even in there?
First, we find the derivative of x square plus y square.
Yeah,
Equals-
yeah. If they're wanting you to find a rate, that means you're going to have to take the derivative of something, and it's going to be the no equation or the no formula you stuck in here. So she is right. So that would be 2x dx dt plus 2y dy dt. And then what's the derivative of 25 squared?
0.
0. All right, so now you have your dy dt. So now you can start plugging in your givens. So we know that x is 7. The dx dt is 2. The y we don't have, and we need it so that we can get the dy dt. So how do you get the y?
From Pythagorean theorem.
Yeah, so you're going to go back to the original theorem or the original equation, plug in your x value. And you're going to solve that thing for y. So if you squared out 25, squared out the 7, moved everything over, square rooted it, y is going to equal 24. And we don't know dy dt, so it just stays right where it is. And now you can solve for it. And then you can simplify. Like your 2's cancel out. 2 goes into 24 12 times. So -7/12. And if you just circled this, because some people did that on the quiz, or a previous quiz, I was talking about velocity, I think. They got a point marked off because what's left out?
Units?
The units. So what would the units be?
Is it feet per second?
Feet per second.
Because we're talking about like a height.
Uh-huh. Yeah, talking about height. Okay, and does it make sense that the answer is negative?
Yeah, it's reduced.
Yeah. Yeah, the height, the top of the ladder is moving down, so this side is getting smaller and smaller, so it's decreasing. So if something's getting smaller or decreasing or reducing, that's a negative rate. If it's getting larger and larger, then it would be positive. Okay. All right. Any questions on this one? Take that as a no. Okay, part B. Consider the triangle formed by the side of the house. So same triangle again. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. Okay, so your givens are the same. Like dx dt is 2. The x is 7. That stuff didn't change. But we also know the dy dt. Which is going to be negative 7 over 12. Because that was the rate, or that's the rate that we found when x was 7. Okay, so what formula would go in the no?
The area formula?
The area formula. So what's the area of a triangle? For this triangle, I guess.
X times y divided by 2.
And find the rate at which the area of the triangle is changing. So that means you're trying to find
d of a over dt.
Yeah, dA dt. So to get that dA dt to show up, you need to get or take the derivative of the area. So dA dt is going to equal 1/2. And then when you do the derivative of xy, you're going to have to use what?
Product rule.
Product rule. Okay, so the derivative of x is going to be
1
times
y
dx
not
dt.
quite. But you didn't finish the derivative of x.
Okay, it's 1 dx dt.
Yeah. Times the y, and then plus the derivative of the y would be your dy dt times the x. And now just start plugging in all of our stuff. So dx dt was 2. The y is the same y that we found earlier, which was 24 from part A. dy dt is negative 7 over 12. And our x was 7. Ugh. That's a fun fraction. So we have 48 minus 49 over 12. Everybody know what that is off the top of their head? Okay, 527 over 12, or 527 all over 24. And we just need one more thing. So what thing do we need?
Our units.
The units. So what are the units with this? And they're not the same units as they were in part A.
Feet squared per second.
Yeah, feet squared per second. So how do I know it's feet squared?
Because it times the xy.
Because it's area.
Because it's area. So area, the dimension or the units for area is always like feet squared or meters squared. So it's always the length squared. So the rate is the same thing. So feet squared per second. Okay, then part C, find the rate at which the angle between the ladder and the wall of the house is changing. So this is another place where I see a lot of students make an error because they don't, they look at the wrong angle. So it's between the ladder and the wall of the house. So it sounds easy, but a lot of people put the theta or the angle in the wrong spot because they don't know which side is which. So which side is the ladder?
25.
The 25. And which side is the wall of the house?
Y.
The Y. So if it's in between the ladder and the wall, that means it's this angle right there. Okay, so the formula that you choose for here has to involve the theta in some way, which means you're going to have to use what kind of a function?
Trig function.
A trig function. And you can choose any of the trig functions that you want. So you have 6 of them. You just have to pick one of them. They will all work. Some of them are a little nicer than others, but they will all definitely work. So it just depends on what you choose. The nice ones are the ones that only involve one letter. So pick a trig function. that would hopefully only involve one letter.
Fine.
Sine.
Sine. Okay, so sine of theta, if you go with SOHCAHTOA, that's going to equal what over what?
Opposite over a hypotenuse.
Mm-hmm. So the hypotenuse is 25. What's the opposite of the theta?
X.
The x. Okay, our givens are the same thing. Dx dt is 2. X is 7. We know dy dt is negative 7 over 12. Actually, I don't think we need the y's. This is not in there. And then the find, what do they want you to actually find?
D theta.
D theta dt.
D
dt.
theta dt. Yeah, find the rate at which the angle is changing. So d theta dt. Okay, so go back to the no and take the derivative of it. So the derivative of sine is
Cosine.
cosine. The derivative of theta, or the angle,
D theta all over dt.
yeah. And then the x over 25, a lot of people will want to use a quotient rule because they just have it stuck in their brain that every time they see a fraction, it requires a quotient rule. But if it's a constant down there, then you don't have to use it. It's the same thing as like 1 over 25 times x. So you don't need to use the quotient rule with it if you don't want to, because the derivative of 1 over 25 times x would just be what?
One over 25.
Yeah. 1 over 25 times dx dt.
Dx dt.
Yeah. Okay, so now we have the d theta dt, which is good because we're trying to find it. So now we can plug in the dx dt, and then we're also going to plug something in for the cosine of theta. So cosine of theta is going to come from the triangle with all the sides labeled. So the 25 for the ladder, 7 for the ground, and the 24 for the wall. So if we use this triangle into cosine of that triangle, it would be
24 over 25.
24 over 25. And then our dxdt was 2. Okay, so now just solve for d theta dt. Multiply by 24, 25 over 24. And what
I kind of lost you. Did you ask a question?
oh, so what are the units?
Is it radians?
Radians
Second?
per second, yeah. Um, so I'm pretty sure I mentioned this in the videos. but the default mode for angles is radians. The only time you use degrees is if it actually tells you in the problem, but if it doesn't say anything about it, then you're always going to be in radians. So calculus, it's like you're pretty much in radians most of the time, but when you go into physics, you're pretty much in degrees most of the time. So just be aware of that if, oops. Just be aware of that if you're taking both at the same time. All right, we have a couple more minutes left. What else do you want to ask about?
I had a question, Professor Jordan.
Yeah.
I was looking at a problem from my Math S80 course, and it was, related to section 3.7, and it was asking for finding the altitude, the rate of change for the altitude of a plane flying 375 miles per hour. So I drew it out and went to work to solve it, and hit a road bump. So I did a little research, and it advised, because the trig function was acting as a coefficient, to not take the derivative of it. But I would take like the derivative of other values. And I didn't quite understand why I wouldn't take the derivative of the trig function in this problem.
It's like without seeing it and kind of going off of what they said,
Okay.
it might be because the theta was constant.
Yes, that's correct.
Okay. So, and if it's a constant, like if you had like y equals 2x, like that, what's your derivative? Or, well, let me,
2.
let's try x squared.
2d. Okay. 2x.
Like it'd be just 2x. And then if it was
2x.
Hang on, I lost my train of thought. So, okay. Oh, yeah. All right. So y equals 3x, the derivative would just be 3. Y equals 4x, the derivative is just 4, right? Because that's just the constant that's out in front isn't affecting, it just stays there.
Mm-hmm.
So let's just say it was like cosine of, I don't know, 30 degrees times x. Your derivative would still just be cosine of 30 degrees. Because cosine of 30 is still a constant, it's not a variable. Does that make sense?
Kind of. I mean, just without, I guess, the context of the problem, letting me know that as the plane's flying, it's moving, at an angle of 30 degrees constantly at so many miles per hour. But just looking at this, I would think, oh, I should do the product rule. Like take the derivative of cosine of 30, x plus derivative of x, cosine of 30.
Okay.
So, I mean, is that right? Or
yeah.
would I?
So that's right, but what's the derivative of any constant? Be 0.
Itself? It's here. Oh.
No, the derivative of just a constant just on its own is always 0.
Okay.
So if you are doing the derivative of cosine of 30, that whole thing right there, that's your constant. So the derivative of cosine of 30 is just going to be a 0. So you can
Out of the context of the problem. Is that what you're saying?
Well, yeah, because the derivative of any constant is a zero no matter what. Oops. So the only, if you're trying to do the derivative of a trig function, it's because there's an angle in the trig function. But if the angle is an actual number, it's no longer a variable, it's a constant.
Oh,
Because
okay.
because like sine of 30, you can evaluate that. That's just a half. Sine of theta, you can't evaluate because you don't know what theta is. Or the same thing of like cosine of 30. That's just √3/2. So for your problem, if it was flying at a constant angle of 30 degrees, right?
It was at 22.
22 degrees. Okay. Was it using sine or cosine or tangent?
I mean, I used sine
Sine.
because it was asking for altitude.
Okay.
So
yeah, sine of 22 degrees, you're just going to leave it as sine of 22 degrees. Because it's just
okay.
a number. It's some decimal. But you can just leave it as sine of 22. So if it was just y equals sine of 22 degrees times x, your derivative is just sine of 22 degrees. Which is weird, but you can't evaluate it any further.
Okay, thank you.
Yeah. Okay. Well, oops. I think that is gonna do it. So I hope this helped. And if it didn't, I'm sorry.
Can I email you my question on problem 29, the lamppost problem?
Sure.
Okay.